Hello everyone, and welcome back to more fun times with right triangle trig specifically, and we're going to do some other theorems from geometry that are going to make a lovely appearance. First though, before we do anything with trig functions, I want to remind everyone about this word reciprocal. Now, if I wrote down a number like 4/5, I'm sure a lot of you would say, okay, the reciprocal is 5/4, and I agree with you. But I want to remind you about the definition, that a reciprocal is technically 1 over the number. So in this case, if the number is 4/5 and the reciprocal is really 1 over the number, that really means 1 divided by 4/5. This notation is not very helpful though. So you could think of it instead as 1 divided by 4/5, and dividing by a fraction is the same as multiplying by the reciprocal. So this could really be 1 times 5/4, which is where the 5/4 came from in the first place. Now, the reason I mentioned reciprocal at all is to transition into the new trig functions we're going to learn. They are called cosecant, and that is the reciprocal of sine, secant, which is the reciprocal of cosine, and cotangent, which is the reciprocal of cotangent. Here's why. Let's look at sine, for instance. Sine is opposite over hypotenuse, but if you took, by the definition of a reciprocal, 1 over opposite over hypotenuse, that is the same as 1 divided by opposite over hypotenuse, which could be written as 1 times hypotenuse over opposite, which is where cosecant comes from. So notice, opposite over hypotenuse becomes hypotenuse over opposite. So these two are reciprocals. Cosine and secant, these two are reciprocals because adjacent over hypotenuse becomes hypotenuse over adjacent, and tangent and cotangent are reciprocals for the same reason. So I would say sooner rather than later, it would be a good idea to memorize that cosecant goes with sine, secant goes with cosine, and cotangent goes with tangent. Now, let's actually apply these to a right triangle. This might remind some of you of an example we did in the other video about right triangle trig. And you might notice that we are yet again missing a third side. So we could rely on the Pythagorean theorem. So we could say x squared plus 6 squared equals 10 squared. X squared plus 36 equals 100. X squared, if you subtract 64, would be equal to 64. So if we took the square root, we would get that x is 8. Now, some of you might have liked those Pythagorean triples. So if you notice that 6 and 10 are both could be divided by 2, this is technically a 3, 4, 5 triple that was multiplied by 2, just as a fun fact. So now if I come back to my trig functions, I want to plug in an angle and get out a ratio. Just like yesterday, we want to rely on where the angle is positioned. So that means that the 6 is opposite of the angle, the 8 is adjacent, and the 10 is the hypotenuse. So if I'm looking at sine, that is defined as opposite over hypotenuse. So in this case, that would be 6 over 10, which could be reduced to 3/5. Now, without doing much work, sine and cosecant are reciprocals, so the cosecant ratio would be 5 over 3. Cosine of this same angle. Cosine is adjacent over hypotenuse, which in this case would be 8 over 10, which is reduced to 4 over 5. But then the reciprocal of that is secant, which the ratio would be 5 over 4. Tangent of this same angle is originally 6 over 8, which can be reduced to 3/4. So the reciprocal here would be 4/3. So once you get these definitions down, you might notice how much the original trig functions help you find everything you need. One more example like this, given that the sine of alpha is 5/6. This time you're not given a picture, but that's okay. We can still work with it. Because we know we're in the right triangle trig unit or sections here, we can draw a little right triangle. So here's my situation. If I rewrite sine of alpha equals, instead of a sideways fraction, if we write a vertical fraction, remember that sine is opposite over hypotenuse. So if I call alpha this bottom angle, just as a reference, the opposite of alpha would be this side. So that, according to this, would have to be 5, because this is the opposite. And then the hypotenuse is always across from the right angle. So this would have to be my 6. And so just like before, we'd have to find our missing side. So, good old Pythagorean theorem again. X squared plus 5 squared equals 6 squared. X squared plus 25 equals 36. If I subtract 25, I would get 11. So it seems like I'm getting a glorious answer of x equals the square root of 11. Little ugly, but we can handle it. So if we wanted to find our trig functions based on alpha, which I put down here, the sign, again, is opposite over hypotenuse. So in this case, opposite is 5, hypotenuse is 6, which was given. So that means that the cosecant, the reciprocal, would be 6/5. Cosine of alpha would be adjacent over hypotenuse. So in this case, adjacent to this angle is the square root of 11 over the hypotenuse, which is 6. So the secant reciprocal would be 6 over the square root of 11. Now, I would make sure to ask your teacher, but I know that I like to keep my answers rationalized. Some of you might remember in geometry that you technically cannot have a square root in the denominator. So what you would do is multiply the top and bottom by the square root of 11. So you'd have 6 times the square root of 11 on top, and then the bottom would be square root of 11 times square root of 11, which is technically the square root of 121, and the square root of 121 is just 11. So you do this so that you don't have a radical in the denominator. Tangent of alpha and the cotangent of alpha. If I'm using this as a basis again, tangent is opposite over adjacent. So the opposite is 5, and the adjacent side would be the square root of 11. So this is something we're eventually going to have to rationalize. However, before I do that, the cotangent of alpha is the reciprocal. So the cotangent would be the square root of 11 over 5, which doesn't have a problem because the square root is in the numerator, not the denominator. Just like this example, I'm going to multiply top and bottom by the square root of 11. So I would get 5 times the square root of 11 on the top. On the bottom, square root of 11 times square root of 11 is again square root of 121, which is 11. So that reduces to 5 square root of 11 over 11. And I'm going to box my final answers, or my final ratios. The next part of this video is reminding you of something from geometry that I really enjoy, something called special right triangles. And they were the 30, 60, 90 and the 45, 45, 90 triangles. And some of you might actually remember the relationships. So what I want you to do is take a minute and see if you can remember anything about these special right triangles. Let me give you some time. Well, if we start with this 30, 60, 90 triangle, some of you might remember that this has to be the smallest side of our triangle because it is across from the smallest of the 3 angles in the triangle. We usually call the smallest side x. The medium side of the triangle, which is across from the medium degree measure, which is 60, which is smaller than 90, was root 3 larger than the smaller side. So if this was the smaller side, you take the smallest side times root 3. And then the hypotenuse ended up being double of the smallest side. So we symbolize that as 2x. So what's really nice is if you have the smallest side of a 30, 60, 90, you can just take that side, multiply that by root 3 to get this side, and multiply it by 2 to get the hypotenuse. For the 45, 45, 90, I find this intriguing because in geometry, some of you might remember that this is called a right isosceles triangle because these 2 angles are congruent, these 2 sides are as well. And so they were also called legs rather than sides. So if we call this side x, we could also call this side x. And so the hypotenuse ended up being, actually because of the Pythagorean theorem, x times the square root of 2. As a memory trick, and I will mention this later as well, what I do is a lot of students forget which one has the root 3 and which one has the root 2. I say to myself, because this has a 30-degree angle, has a 3 in it, that's why there's a root 3 here. And because there are two congruent sides, that's why there is a root 2. That's at least a nice memory trick. Now, you might be saying, why are these lovely triangles coming back and making an appearance? Well, they're actually going to help us with some right triangle situations and some trig later on. For instance, if I want to find the sine of 30 degrees, I'm going to use this triangle as a basis. So 30 here would be my reference, and I would say, all right, I need to make a ratio because angle in, ratio out. Even though we have everything in terms of x, that it doesn't have to stop us. Sine is still opposite over hypotenuse. The opposite of 30 is x, and the hypotenuse compared to 30 is 2x. Now remember, there's technically a 1 in front of that x, and when you have an x on the top and bottom, they cross out. So the sine of 30 ended up just being the ratio 1/2. The tangent of 45 degrees. Now we're going to use this triangle as a basis. And we have two angles that we could choose from because they're both 45. Let's choose this one just for the sake of it. Tangent is defined as opposite over adjacent. The opposite side is x, and the adjacent side is also x. So just like the last problem, this would really be 1x over 1x. The x's would cross out, so your ratio will be 1 over 1, or just 1. Last two, just for simplicity, I'm going to recopy the relationships x root 3, 2x, x root 2. And what we want to do is find the secant of 60 degrees, so we use 60 as our reference, and cotangent of 45, so we use 45 again as our reference. I am going to ask you to pause the video and try these first, but before I do that, I want to remind everyone that the reciprocal of secant is cosine. So you might consider finding the cosine first and then finding the reciprocal. And the reciprocal of cotangent is really tangent. So you might want to consider finding the finding tangent first and then finding the reciprocal. So here's your chance. I'm going to pause again. And when you come back, I will have my work at least started and I will talk you through the final answers. All right, guys, so to check your work, what I did first for the secant is I found the cosine of 60, because a lot of you are more familiar with cosine at this point. Cosine is adjacent over hypotenuse, so if this is my reference, adjacent was x, and the hypotenuse was 2x. So like the last example, I put a 1 in front of the x, crossed the x's out, and ended up getting a ratio of 1/2. However, the problem did not ask for cosine, it asked for the reciprocal of secant. So I took 1/2 and I found the reciprocal of 2 over 1, or just 2. The cotangent of 45 reminds me of the problem we did on the previous slide. The tangent of 45 is opposite over adjacent, which in this case, if this is my reference, is again x over x, which is really 1x over 1x. So if the x's cross out, I'm left with 1 over 1. The reason I left it this way is if I want to find the cotangent of 45, the reciprocal of 1 over 1 is still 1 over 1. So my answer is either 1 over 1 or just plain 1. So again, expect some practice in class tomorrow with this. Best of luck, and I will see you next time.